I'm going to start with distance today. So what is the distance between two vertices? So let's say I have two vertices u and v. Then I write d of u and v for the distance between these two vertices. And I want to define it as the length of the shortest path between u and v. Okay, so, or another way of writing this is that the minimum number of edges in a UV path. Now, as I'm writing this, I'm just assuming that my graph is undirected, but the same definition also works for directed graphs. It's just that if you have a directed graph, then the distance from U to V might be different than the distance from V to U, right? But right now, just imagine that it's an undirected graph, and so V of UV is just the minimum number of edges that you need to traverse if you start at U and you want to end up at V. Okay. Based on this, I can define some other things that are useful. So I can define the eccentricity of a vertex U. And this is just going to be the maximum distance from U to any other vertex V. Okay. So the idea is that I start at U and I look at all the other vertices. I look at the shortest path from U to each of these vertices. And I ask, what is the longest path among these shortest paths? That's the eccentricity of U. Okay. Now, based on this, I can also define the concept of a center. So I say that a vertex U is the center of the graph, or is a center of the graph because we can have several centers, if U has the smallest possible eccentricity. So U is a center if for every vertex V, eccentricity of U is less than or equal to the eccentricity of V. Okay. And also, we have another word here, which comes from geometry, which is kind of ironic because we want to not talk about geometry, but we get our vocabulary from geometry. We define the radius of a graph. And we say that the radius of a graph is basically the minimum eccentricity. So if U is a center, then the radius of my graph G, is just defined as the eccentricity of U. Okay. So U is a center, which means that if I start at U and if I always take shortest paths, all the other vertices are kind of close, at least closer than if I started at any other vertex, right? And then I have this definition that the radius of G is like how far I can go from my vertex U. Now, the intuition here comes from geometry, of course, and it comes from the idea of points in a circle. So let's say I have a circle and I have a bunch of points here. For every 2 points in the circle, I can define their distance, right? That's just the Euclidean distance. And then the eccentricity of a point would be the distance to the farthest point. So if I don't know, let's say here, maybe the farthest point is somewhere here, and this would be the eccentricity of this point, okay? And then the center is, of course, the center. This is the point with the smallest eccentricity. And then the radius is the eccentricity of the center, right? So basically, the idea is that if these points were my vertices in a graph, I have this vertex U, and I have this radius, let's call it R, and every other vertex is within a distance of R from U. But again, kind of weird that we're using words from geometry, even though we don't really care about geometry when we're working with graphs. But then we continue this, and we also define the diameter of a graph. So I have the radius of a graph. I can also define the diameter, and I say that the diameter, let's call it something like this. diameter of G. I want to say that this is the maximum distance between any pair of vertices. So it's the maximum over all possible UV of D of UV. Okay. And the idea here is also based on the intuition from a circle. So if I have 2 points that are as far away from each other as possible in a circle, then the distance between them is the diameter of the circle. Okay. Okay. So we defined all of these things because we want to prove some theorems based on them. So here's my first theorem. I want to say in every graph G, and of course here again I'm talking about undirected graphs, I have this. I have that the radius of G is less than or equal to the diameter of G, which is less than or equal to twice the radius of G. So feels kind of familiar from basic geometry again, but we're talking about graphs here. Why is this the case? So one of the inequalities is pretty obvious, right? So if you look at the definition for the radius of G, this was basically the maximum eccentricity, right? So the radius of G is going to be, at the end of the day, the distance between two vertices, because eccentricities were defined as distances between vertices taking some maximums. And then here, I'm taking one of the eccentricities as the radius. So the radius is one of the distances in my graph. So there are two vertices U and V in my graph whose distance is the radius of the graph. But what was the definition of the diameter? The definition of diameter was the maximum distance. So the diameter has to be greater than or equal to any distance in my graph, including the radius. So this part is kind of trivial. This is trivial by definition. Because, again, the radius is a distance and the diameter is the maximum distance. But why is my diameter always at most twice the radius? So let's look at this. Let's say, suppose the distance between two vertices, U and V, is the diameter of G. So I'm choosing two vertices that give me the diameter. I'm going to have this vertex U, and I'm going to have a path from U all the way going to V. And the length of this path is the diameter. Okay. Now, again, this is not unique. I might have many choices of U and V. I might have many choices of what path I take between U and V. Maybe there are several paths of the same length, of the length diameter of G between U and V. I'm just picking one, right? But this is also the shortest path between U and V, right? Because we're only looking at shortest paths. When we were talking about the diameter, we said it's the maximum of the distances, and the distance was based on the shortest path between U and V. So this is, if there are several shortest paths, I don't know, but this is definitely one of the shortest paths between U and V. Now, what was the definition of radius? Radius was the eccentricity of a center. So I have a center, let's call that center C. And by the way, I'm showing C as a different vertex, but maybe C is U or V. I don't know. I don't know that C is a separate vertex, but let's say this is my vertex C. Now, so let's say I chose C such that the eccentricity of C is the radius of my graph. What does this mean? This means that if I look at the distance from C to all of the other vertices, all of these distances are going to be at most the radius of G. Okay. But I can also look at the distance from C to U, and I can look at the distance from C to V, right? And this is at most the radius, and this is also at most the radius. So I have a path from U to V. From U go to C, from C go to V. And this is going to take at most twice the radius, right? But I know that this path, which was the diameter, was the shortest path from U to V. So the length of this path should be less than or equal to the length of this walk. Actually, I'm not sure this is a path. It might be a walk, but not a path. But then we have that famous lemma that whenever you have a UV walk, it includes a UV path in it, right? So in any case, I found a path from U to V whose length is at most twice the radius of G. But I know the distance from U to V is the diameter of G, so the diameter has to be at most twice the radius. So we want to now look at trees and see what happens with the radius and diameter of trees, or actually what happens with the centers of trees. I think the radius and diameter thing is actually in your problem set. So here's another theorem. Let's say that T is a tree with 3 or more vertices. So I have at least 3 vertices. If T is a tree and it's not just a tree with 1 vertex or 2 vertex, then no leaf is a center. So let's say I have a simple tree here. Okay. I can ask for every vertex, what is its eccentricity? So from this vertex, how far can I get? The eccentricity of this one is 2, right? The eccentricity of this one is also 2 because I can go up and then left. The eccentricity of this one is actually 3, and this one is also 3, and this one is 3. And as you see, in this case, my centers are these 2 vertices, and none of them are leaves. So I'm saying that if my tree is big enough, if I don't have the case where it's just like, this is my tree and everything is a leaf. If I don't have that case, then no leaf is going to be a center. Which again, kind of makes sense intuitively because the idea was that the center is really a vertex that is quite close to everything else, right? And if you think of a tree, a leaf is pretty much the opposite of that. It's a vertex that is far away from everything else. So I want to show that no leaf is a center. Let's try to prove this by contradiction. So I say, suppose that L is a leaf and a center. Okay. What do I know about this vertex L? I know that it's a leaf. So I know that the degree of L is 1. So L has an edge to some other vertex, let's call that U. And this is the only edge coming out of L. And then here I have the rest of my tree, however it looks. I don't really care. I have the rest of my tree. Okay. But what does this tell you? If I want the distance from L to any other vertex, so just take any vertex here, V. If I want to go from L to V, I have to go through U, right? So the distance from L to V is going to be 1 plus the distance from U to V. And this is the case for every vertex, right? Every vertex other than L itself, of course, but every vertex here. So this means that the eccentricity of U is less than the eccentricity of L. So L cannot be a center because U would be a better choice for a center. Okay, great. But now we want to prove something more interesting. This is also about trees. So I say let T be a tree. Now, I want to say, look at all the centers of T, because previously we've seen that the center is not unique. I can have a graph that has many centers. Oh, actually, if you think about it, if I have the complete graph, for example, every vertex is a center, because the distance from every vertex to every other vertex is 1, right? So I can have many centers, but let's say I have a tree. And if T is a tree, I want to say that I either have only one center, or I have two centers that are connected to each other by a single edge. So if T is a tree, T either has one center, C, or two neighboring centers. Let's call them C1 and C2. So I'm saying that if I have a tree, I cannot have more than two centers. And also, if I have two centers, they're going to be neighbors. I'm going to prove this using the weirdest kind of induction you've seen so far in this course. I'm going to do an induction on the size of my tree. So when I'm doing induction on the size of the tree, it doesn't matter if I say I do induction on the number of vertices or the number of edges, because the number of edges is always one less than the number of vertices, right? Because it's a tree. So I can just say I do induction on the number of vertices or induction on the number of edges. It's the same. And I'm going to do strong induction. So I say strong induction on n, where n is the number of vertices. Okay. So my base cases, look, I want to be able to use this previous theorem, and this previous theorem only works if I have 3 or more vertices. So as my base cases, I want to take the case where I have one vertex and two vertices. Okay, so if I have one vertex only, then this vertex, this is a center, right? If I have two vertices, the only tree that I can have with two vertices is the tree that just has one edge connecting the two. And of course, you can see that both of them are centers. Right? Because the eccentricity of each of them is exactly 1. So these are my base cases. But now I'm going to do the induction step. So in the induction step, I'm going to assume that n is at least 3. Right? Because I've already covered the cases where n was 1 or 2. So let's say I have a tree, and this tree has more than 2 vertices. Okay, so let's say this is my tree. And it has more than 2 vertices. Okay. So what do I know about centers? I know that none of my leaves are centers. So what I want to look at is what happens if I remove all the leaves. Okay. So if I remove all the leaves, I'm not removing any of my centers. So I might be able to find the center in the remainder of the graph, hopefully. Right? But also, what happens to the eccentricity of the remaining vertices? So let's say I have a vertex here. Let's say I have some vertex V here. Right? It has some eccentricity. In this case, I think the eccentricity of V is 1, 2, 3, 4. Right? So the farthest I can go from V is 4 edges. Right? What happens if I remove all of the leaves? What happens to the eccentricity of V? It decreases by exactly 1. Okay. Now, we can kind of prove this as a separate lemma, but it's too similar to the lemmas that we've had before. So the reason it decreases by 1 is that if you consider V, and if you consider the longest path that goes out of V, so I want to start at V and take the longest possible path, it has to end at one of the leaves. Because if it doesn't end at a leaf, I can just find a way of extending the path. Right? So because the longest path ends at a leaf, so in this case, the longest path or a longest path going out of V will end at this leaf. When I remove this leaf, then I have a longest path that ends at the neighbor of this leaf. So the eccentricity goes down by exactly 1. But this is great because it means that if I remove all the leaves, the eccentricity of every other vertex goes down by 1. So a vertex that was a center before is a center after the removal of the leaves and vice versa. Okay. So this is great. I just remove all my leaves. Okay. Remove all leaves. And let's say that this converts my tree T into a new tree T prime. Now T prime is smaller than T. And removing the leaves does not change the centers. Because T prime is smaller than T, by induction hypothesis, the center of T prime is either 1 vertex or 2 neighboring vertices. They're going to be the center of T as well. Okay, that's the proof of it. So basically, the idea is very simple. I'm going to start by removing all the leaves. So this is the first step. I'm just removing all the leaves. Okay. And then in the second step, I again remove all the vertices that are now leaves. So this one is now a leaf, I remove it. This one is a leaf, I remove it. This one is a leaf, I remove it. This one is a leaf, I remove it. And if I continue this, in the end, I'm going to either have either 1 vertex or 2 vertices, and those are going to be my centers. So it's a very simple algorithm. In this case, I have 2 vertices remaining. These are centers. And of course, the proof by induction shows that this is. Okay. But now let's talk about actually finding distances between vertices. So this is the first problem that I want you to consider. Suppose that I have an input, which is just a graph G, and some particular vertex U. So, and U in the set of vertices of G. And as the output, I want you to give me the distance from U to every other vertex. Okay, so I want you to give me D of UV for every vertex V. Okay. This is called a single source shortest path problem. Because the idea is that I have a vertex U, which is my single source, and I want to know what is the distance from U to every other vertex. Okay. Actually, the algorithm we're going to use for this is something that you've seen in a different context before in this course when we wanted to find a spanning tree, right? So when I wanted to say that every connected graph has a spanning tree, I actually used BFS, and this is the same thing that I want to use here. So our algorithm is what we call breadth first search. For BFS. Now, this is a very simple algorithm. The idea is that I want to create a hierarchy, a bunch of layers, and I want to divide the vertices in these layers, and every layer will correspond to the vertices that have a particular distance to my root U. So I'm going to say I start with my vertex U, and of course the distance from U to U is 0, right? And then I look at all the neighbors of U. I add all the neighbors of U in the next part, in the next layer. So this is the layer where the distance is 0. I'm going to have another layer, and these are all the vertices where the distance is 1. Okay. So these are basically all the neighbors of U. And then I look at the neighbors of U. So I look at the neighbors of all the vertices who were in layer 1, and I add those to layer 2. Now, it's possible that I look at the neighbors of this vertex and I see another vertex that was already in layer 1. I will not change that layer. So I just find new vertices and I add them to the next layer. So I start at U, I add its neighbors to layer 1. I look at the neighbors of neighbors and I add them to layer 2. Okay. So layer 2 is all the vertices that have a distance of 2 to my root. And I just continue this. I continue this until I see all of my vertices. Or to be more precise, until I see all the vertices that are in the same connected component as U. And of course, if a vertex is not in the same connected component as U, we can just say the distance is infinite. We can never get to it, okay? Now, some small points here. It's possible that a vertex, for example, here in layer 2, is actually connected to 2 vertices in layer 1. In this case, I don't care. I just choose one of them, right? Because there are like 2 ways of reaching this vertex with a distance of 2. I don't care about that. All I care about is what is the minimum distance from U to this vertex, and it's 2. And of course, this also gives me a tree, and this is a tree rooted at U. We call this a BFS tree, or we can also call it a shortest path tree, because if I give you any other vertex, let's say I give you a vertex V, and I ask you what is the shortest path from U to V. I'm not just asking for the distance, I'm asking for the path itself. It's just the path in this tree that goes from U to. Okay. Great. So this is how we can solve our problem. Basically, given a fixed vertex U, we can find the distance to every vertex V. Now, if I wanted to find all the distances, I can just do this for every U. So I can just create n different BFS trees. And every time I start my BFS at one of the vertices and I create this tree, find the distance from that vertex to every other. Okay. But now I'm going to give you another way of looking at this. So here's another solution. By the way, in 3711, you're going to see a runtime analysis of these solutions, and you're going to see in which cases you should use each one of them. But in this course, we don't care. We're just assuming that our computers are infinitely fast. So as long as we have an algorithm that works, we don't care how much time it takes. But this is only in this course. Okay, here's another solution. I want to somehow find a recurrence relation for the distances. Okay. And here's what I can do. I can say D of U, V, and K, I'm just adding a K at the end, is going to be 1 if there is a path of length K from U to V. And it's going to be 0 if there is no path of length K. Okay. Or actually, let me see. It's better to talk about walks here. Okay, so this is 1 if there is a walk with K edges from U to V. And it's going to be 0 otherwise. Okay, so like this. Okay. How can I compute these values? So, and of course, then when I want to find the shortest path between U and V, I just try every K and I see what is the smallest K where D of U, V, K is 1. Right. Or actually, maybe instead of D, let me give it another name because we're using D for degree, distance, everything. So whatever, let's call it A of U, V, K. So A of U, V, K is 1 if there is a walk with K edges from U to V, and it's 0 otherwise. And then I can easily say that D of U, V is going to be the smallest K such that A of U, V, K is 1. Okay. So if I compute these A values, I can easily compute the D values. Okay, now let's say I want to find A of U, V, and K. What does this mean? This means that I'm asking, if I start at U, is it possible to take K edges and get to V? Okay. So what I can say is, suppose I'm reaching V with K edges. What does that mean? That means that I should reach one of the neighbors of V with K minus 1 edges, and then take an edge from that neighbor to V. Okay. So I can say, look at V and look at all of its neighbors. Okay, let's say the neighbors are W1 to WT. And then ask, can I start from U and get to one of these neighbors in K minus 1 steps? If I can start from U and get to one of the neighbors in K minus 1 steps, then I can get to V in K steps. Okay. So A of UVK is basically 1 if there exists some neighbor W, neighbor of V, such that A of UWK minus 1 is 1. And it's 0 otherwise. Okay. By the way, again, I'm just working with undirected graphs here. You can easily extend these ideas to directed graphs. Or another way of writing this, because I don't like to write like this, is that, remember at the very beginning of this course, we talked about this idea that 0 means false and 1 means true, right? So A of UVK is going to be the OR over all W's that are neighbors of V of A of UWK minus 1. Great. Now I have a recurrence relation for A of UVK. If I have a base case, I'm done. And the base cases are very easy. What happens when K is 0? A of U0 is 1, because if I start at U with 0 steps, I can be at U. But if I can take only 0 steps, then I cannot go anywhere else. So for every vertex V that is not the same as U, A of UV0 is going to be 0. So those are my base cases. And I'm too lazy to write them. Okay. Great. But is this interesting? Why would this be interesting? Does this help us in any way? Why couldn't I just do the BFS? Well, suppose that I want to extend my problem to say that I now have weighted graphs. Okay. So consider a weighted graph. And consider that I have basically a weight function that assigns a weight to every edge. If I have a weight function that assigns a weight to every edge, then when I talk about the shortest path or the distance, I no longer mean the number of edges. I mean the sum of the weights on the edges. So the length of a path, so length of a path is going to be, let's say this is a path P, it's going to be the sum over all edges in P of the weight of that edge, right? And then the distance from a vertex U to a vertex V is going to be the minimum over all paths. Actually, instead of paths, I can again say walk here. Doesn't really matter for these definitions that much. So it's going to be the minimum over all walks of the length of that walk. So then we call it L of P. So L of P. Okay. Now, as soon as I do this, As soon as I have weights, I can no longer use my BFS algorithm. Right? Because this whole idea of breaking it down into layers only works if the distances are 0, 1, 2 to n. Right? But when I have weights, my distances can be anything. I don't even know what exactly they can be. They can be any real number. And more interestingly, I can have a situation like this. So let's say I have my vertex U, I have V, and then I have W. And let's say the distance from the weight here is 1, but the weight here is -10. Right? So now U is closer to W than it is to V. Because the distance from U to W is -9. The distance from U to V is 1. Right? Yes. But if we use Vox, that's not the case. You're right. Yeah, I know that's what you want to say. Yeah, so if I'm talking about Vox here, actually, as soon as I have a negative edge, I can go over this negative edge over and over again. I can get -infinity. So yeah, maybe not a good idea to talk about Vox here. Maybe let's say lengths of a path, right? But if I don't have negative weights, then it doesn't matter if I put a Vox here or. Okay. Great. But in any case, as soon as I have weights, my BFS algorithm does not work anymore. But let's see if this second algorithm can somehow be made to work. So here I was saying A of UVK is just a Boolean. It's going to give me 1 if there is a block with K edges, and it's going to give me 0 otherwise. Let's say instead of this, I extend it and I say, what is the length of the shortest walk with K edges? And again, it makes sense because now my length is not the number of edges. So I just say, look at all the walks with K edges, which one has the shortest length? And let's call that shortest length A of UVK. Okay, so I'm going to say A of UVK is going to be the length of a shortest walk with K edges from U to V. Okay. And also because I don't want to constantly have to think about walk or path or so on, let's just assume that all of my weights are non-negative. Negative weights are going to be a huge hassle for us. We will come back to them after we're done here. So, because now I can say the length of a path or the length of a walk or so on, and then I want my shortest walk to be a path, and this only holds if I have this, right? So I'm going to say A of UVK is the length of the shortest walk, which is also the shortest path, with K edges from U to V. Okay. Now I can do something similar to before. So first of all, A of UU0 is 0. So if I start at U and I want to end at U and I want to take no edges, what is the minimum total weight? It's 0. What about the case where I have two different vertices? So A of UV0, what should I put here? Yeah, so it's impossible. I cannot go from U to V with 0 edges. But when it's impossible, I'm going to say the distance is infinite. Right. So if I look at all the shortest walks from U to V that have 0 edges, that's the empty set. And I'm going to just define that the minimum element of the empty set is plus infinity. Okay. Basically, just think of plus infinity as saying that no such walk exists. Whenever there is no such walk, I put plus infinity. Okay. Now, let's consider the cases where K is at least 1. I want A of UVK. So I have U, I have V, I want to go from U to V, and I want the length here, but sorry, the number of edges here to be K, but I want to minimize the length. Okay. Now, again, I can do a casework. I can say, well, if I'm getting to V with K edges, I should get to one of the neighbors of V with K minus 1 edges, right? So if I have a bunch of neighbors here, I should get to one of them with K minus 1 edges. Let's call these neighbors, I don't know, V1, V2 to VT. I should get to one of them with K minus 1 edges, and then from there, I should go to V. Okay. But what is the cost of that? What is the length of the path that I will have to take? Well, if I want to go to, let's say, VI, I have to start at U and go to VI with K minus 1 edges. And of course, I want to take the shortest possible path with K minus 1 edges, which is what I have. Well, its length is what I have in A of U, VI, K minus 1. But then I have to take the edge from VI to V. And that edge has a weight. So this would be plus the weight of the edge from VI to V. Right? And of course, I want to minimize this. So I take the VI that gives me the minimum value. So this is the minimum over every VI that is a neighbor of V. So you see, this algorithm actually extends. So now I can find these things. And then, of course, if I want the shortest path overall, I just go. So let's say I have U and V. I want to know what is the length of the shortest path from U to V. What can I do in that case? I can just try every possible K. I don't know how many edges my shortest path from U to V is going to have. So let's just try every possible value. Right? And every possible value is going to be between 0 to n minus 1, right? Because I'm talking about paths, and if I have n vertices, I cannot have a path longer than n minus 1. Great. But interestingly, this is matrix multiplication. Do you see that? So here's the thing. Suppose that I look at my adjacency matrix. So let's say I have my adjacency matrix A. But I'm going to change my adjacency matrix to also have the weights in it. Okay. So I'm going to say, if I look at entry IJ, I actually prefer the C++ notation here instead of using the mathematical notation. So I'm going to say Aij is the weight of the edge from I to J. Okay. If such an edge exists. And if there is no edge, I'm just going to put infinite. Okay. So let's do an example. Let's say I have this graph. By the way, this is called the house graph. I mean, if you rotate it, it's kind of like a house. So I have my vertices 1, 2, 3, 4, 5. And let's say I have some weights on the edges. So 2, 6, 1, let's say 0 here just for the fun of it. And actually, you know what? I'm too lazy to do 5 vertices. Let's do 4 vertices. Okay. So if I want to create my matrix A here, which is my adjacency matrix, basically I'm going to write the weight of the edge. Okay. So I have 1, 2, 3, 4. These are my vertices, and I also have a row for each one of them. From 1 to 1, I don't have an edge. So I'm going to say infinite. From 1 to 2, it's 2. From 1 to 3, it's 1. There is no edge from 1 to 4, so I'm going to put infinite. Okay. 2 to 1 is 2. 2 to 2 is infinite. 2 to 3 is infinite. 2 to 4 is 6. 3 to 1 is 1. 3 to 2 is infinite. 3 to 3 is infinite. 3 to 4 is 0. 4 to 1 is infinite, 4 to 2 is 6, 4 to 3 is 0, 4 to 4 is infinite. This is my adjacency matrix. Okay. Now, do you also agree that what this is giving me is the length of the shortest path with one edge between every pair of vertices? That's basically what my adjacency matrix is. So this Aij here is actually Aij1 here. Right? So this is all my adjacency matrix is saying is what is the length of the shortest path, for example, from 3 to 4 that has one edge. And again, I'm doing this for undirected graphs. You can do it for directed graphs as well. It's just that you have to take care of the direction. Okay. So now, here's what I'm going to do. This is what some of you who have passed algebra already know about. I'm going to look at the tropical semi-ring, or basically, I'm going to look at the min plus semi-ring. What does this mean? This means that, well, when I'm working with numbers, when I'm doing matrix multiplication, I basically have two operations, right? I have addition and I have multiplication. So normally, if I have two matrices A and B, and I'm multiplying them, then, so let's say C is A times B. That means that the element at position Cij is going to be what? It's going to be the sum over every k of Aik times Bkj. Right? That's the definition of matrix multiplication. Now, this definition needs two operations. It needs a multiplication operation and it needs a sum operation. I can change these operations. I can say do it in min plus, which means that instead of doing multiplication, always do addition, and instead of doing addition, always do min. Okay? So I'm going to define a new kind of matrix multiplication, basically, where I say when I write C is A times B in this semi-ring, what I mean is that Cij is actually going to be this. It's going to be the minimum over all k. So instead of addition, I'm doing minimum of Aik plus Bkj. Right? Instead of multiplication, I'm doing plus. Okay? So this is how I'm defining matrix multiplication now. For the rest of this session, whenever I say I'm multiplying two matrices, I'm multiplying them in the min plus semi-ring. I'm multiplying them like this. I've just changed the definition of the two operations. Okay. So we've looked at this matrix A, and we saw that basically if I look at Aij, what it's giving me is the length of the shortest path or shortest walk with one edge from I to J, right? What happens if I multiply this matrix with itself? So what is A squared Ij? So I'm first multiplying A by itself, and then I'm asking what is going to be at the element I. Okay. Let's just use this definition. So it's going to be the minimum over every k of Aik plus Bkj. Oh, sorry. This was also A plus Akj. Now, just think about this. I have a vertex I have another vertex J. Okay. I'm considering every other vertex let's call any of these other vertices k. I'm saying, suppose that I go from I to k. What is the cost of that? And then suppose that I'm going from k to j. What is the cost of that? Sum this up. So this is going to give me the cost of the path that goes from I to k and then to j. But then I'm saying take the minimum over every k. So this is going to give me the shortest walk with two edges that goes from I to j. Right? Now, in general, if I take a to any power, a to the power of t of ij, what is this going to be? I claim that it's exactly this thing that we computed here. So it's going to be a of ijt. So it's going to give me the shortest walk with t edges, the length of the shortest walk with t edges that goes from I to j. And again, you can just prove this inductively very easily because at of ij is what? Well, basically, I don't mean transpose here. This t is like a number, right? I'm running out of variable names. There's no transposing here, okay? Because a to the power of t. This is basically a to the power of t minus 1 times a, okay? So if I write the same thing, it's going to be the minimum over every k of at minus 1 of ik plus a of kj. Right? Now, again, if you want to imagine this, imagine that I want to go from I to j, and I want to take t steps, right? I say, where do I end up after t minus 1 steps? Let's call that place k. So this is the place that I'm going to end up after t minus 1 steps. So I'm going to see what is the shortest walk with t minus 1 steps from I to this place. And then I'm going to say what is the shortest walk with 1 step from this place to j. And I'm going to do this for every possible vertex, right? And I'm taking the minimum of them. So this is going to cover every possible walk with t edges from I to j. And it's taking the minimum weight overall. So this is why this is matrix multiplication. Even though it didn't look like matrix multiplication when I was explaining it like this, what I'm doing here is actually matrix multiplication.
But maybe not a path.
Yes, walks. So again, I'm just assuming that I'm talking about walks. And if your weights are non-negative, then the shortest path will always be a walk, right? So you can just work with walks, and in the end you can. Yeah, and again, this is like the length of the shortest walk with 1 edge from I to j. And this is like the length of the shortest walk with t edges from I to j. Okay. Now, why do I like this? Why do I like this idea of having matrix multiplication? Because this actually makes me able to compute these values faster. So imagine if I just had this algorithm, if I didn't know that this is doing matrix multiplication. I would have to go over every value of k and compute every entry. I had to compute every a of u v k, right? But in the language of matrix multiplication, that's like saying that, okay, compute your adjacency matrix A, and then compute a squared, a to the power of 3, a to the power of 4, so on to a to the power of n. Right? That's what we're doing, or maybe n minus 1. But I don't really need to do this anymore. So suppose that I want to calculate some power of a. So let's say I want to calculate a to the power of 100. Right? I wouldn't just take a and multiply it by itself 100 times. Instead, I can do this recursively. I can say, find a to the power of 50 and multiply it by itself. Right? When I want to find a to the power of 50, I can say find a to the power of 25 and multiply it by itself. When I want to find a to the power of 25, I can say find a to the power of 12, multiply it by itself. You have to also multiply it by a. Right? And so on. So in general, let's say I want to write a function. Let's call it AK or a. I'm really running out of variable names here. AT. So this is supposed to return not the transpose, but a to the power of t. Okay. So how can I do this? I can say, well, if t is 1, then return a. If t is 0, you return the identity matrix, right? And otherwise, if t is even, you just return, well, let's compute another matrix B. Let's say that B is a to the power of t over 2, and you return B times B. Right? If t is odd, then again, let's say that B is a to the power of the floor of t over 2, and you return B times B times A. Okay. So this is much better because instead of having to do n matrix multiplications, I'm actually going to do logarithmically many matrix multiplications. So in order to find A100, I have to find A50, A25, A12, so on. I have to find logarithmically many powers of A. So this is now much faster. And because this is much faster, it gives me everything that I was looking for, right? So if I now tell you, hey, I want the shortest path from vertex U to vertex V. I want to know the length of the shortest path. What would you do? Well, actually, we still cannot use this because if I want the shortest path from U to V, I don't know how many edges that path is going to have. So I still have to find all the powers of A, right? Even though in order to find a to the power of n, I didn't need to find all the powers, but in order to take the minimum over all of them, I have to find all of them. So I have to find a, well, a to the power of 0, which is like the identity matrix, a2, so on. I have to find all of these. And then I have to say that the distance from the vertex U to the vertex V is the minimum over every possible k of AK of U and V. Okay. I'm not happy with this. Because like the whole point was that I don't want to compute all the powers of this matrix A. Okay. Give me a trick so that I can just compute one power of a matrix instead of every power. Yes, but not exactly. So what I'm thinking about is an even simpler trick on the graph itself. So let's say I have this graph, right? So what was a to the power of k of I and j? This is going to be the length of the shortest walk with k edges from vertex I to vertex j. Okay. My problem is that this is only considering the walks that have exactly k edges. But suppose that I want to make it so that it considers walks that have at most k edges. I wanted to also consider walks with k minus 1, k minus 2, so on. Right? If I could do that, then I could just find a to the power of n minus 1 of ij, and I would be happy. Yes. So here's what I'm going to do. This is my trick. Add loops. Okay. So on every vertex, I'm going to add a loop with weight 0 to itself. Okay. So now in this new graph, if in the original graph, I have a walk of length k, let's say from 1 to 4, right? Now in this graph, I have the same walk, but I can just keep taking a bunch of loops and then take that walk, right? So if I just apply the same algorithm to this new graph, I will get a better result. I will get that this k of ij is the length of the shortest walk with at most k edges from I to j, right? So it's the length of the shortest walk with exactly k edges in this new graph, but that's the same as the length of the shortest walk with at most k edges in the original graph before adding the loops. Okay. So I do this trick, I add these loops, and now when I want the distance from u to v, I can just look at one thing. So I can now say d of uv is just a to the power of n minus 1, right? And now I have to just find a to the power of n minus 1, but I know how to find that. I just use this algorithm, this logarithmic algorithm for finding powers of a. Okay. Great. But another thing that would be interesting is to see if I can just extend the BFS. Can I extend my BFS? By the way, it would be interesting to see what you have to change here if you can have negative weights. And actually, if you can have negative weights, you don't have to change much here. It's very easy to see that things still work. It's just that you have to be careful not to talk of paths, just talk of walks. Okay. And also this works for directed graphs as well. You can check those things on your own. But let's say that I have non-negative edge weights, and I want to do something similar to the BFS algorithm. So what was the BFS algorithm doing before? Where is it? It was saying, let's start from the vertex u, and basically let's visit all the other vertices in the order of their distance to u. So let's first find all the vertices that have distance 1, then let's find all the vertices that have distance 2, and so on. So I have now extended the definition of distance. So my distances are no longer going to just be 0, 1, or 2. But I can still have the same idea that, well, I start at vertex u, and I try to find the closest vertex first. And then I try to find the second closest vertex, and so on. Even if their distances are not exactly 1, 2, whatever their distances are some real numbers, but there's going to be a closest vertex. Let's find that closest vertex. And let's keep doing the same thing. Okay, so this will give us an algorithm which is known as Dijkstra's algorithm. Okay, so this is Dijkstra's algorithm. The idea is that in the input, I have a weighted graph G and some vertex, which is my source vertex. And in the output, I want you to give me the distance from U to every vertex, to every other vertex, for every vertex V. Okay. Now, very importantly, I'm assuming that all of my weights are non-negative. So this will not work with negative weights. So I have non-negative weights on edges. So another way of writing this is that down. I have this weight function, W, that maps each of my edges to a weight that is not negative. Okay. Now, the algorithm is very simple. It says, I start from the vertex U, and for every vertex, I keep two things. I keep the distance that I have found, the best distance that I have found to this vertex so far. And I sometimes also keep just a check mark. And I put a check mark on a vertex if I'm sure that the distance to that vertex is never going to change. I found the final vertex, final distance. So the way it starts is that I say the distance from U to itself is 0. And I have a check mark over U. I know that I'm not going to find a better distance for U. Right. And then I say, look at all the neighbors of U. So I have neighbors with different weights, right? So first, update the best distance that you know so far to these vertices. So the best distance that I know to this vertex so far is 1. The best distance that I know to this vertex so far is 4, and this one is 6. And then take the vertex with the minimum distance, in this case 1, and just say that this is definitely the final distance. Put a check mark. Why is that the case? So here's the idea. Look, let's call this vertex V. I have a way of going from U to V and paying only a cost of 1, just taking the edge directly. Is there any way that I can pay a cost of less than 1? No, because if I start from U and I go anywhere else, just in the first step, I'm going to pay more than 1. So no matter what happens in the rest of my graph, I'm not going to find a path that is cheaper than 1 from U to V, right? But I cannot say this about the other vertices. So let's say this vertex is V prime. Right now, I know a path from U to V prime that costs 4. But it's possible that later on, I find another path, maybe starts from V, goes somewhere, comes back to this vertex. And maybe that path has a cost less than 4. Right? Just imagine if all of these edges had a cost of 0, then I would reach V prime with a total cost of 1. But the important point is that if I just look at the closest vertex, if I just look at the vertex V, the distance to V is finalized. It's not going to change, no matter how much I explore the rest of the graph. Right? But then I continue the same thing. I say, okay, I know the distance to V, so I can look at all the neighbors of V. Maybe this one is also a neighbor. And let's say this one has a distance of 2, a weight of 2. This one has a weight of 4. This one has a weight of 1. And now I can update the best distance that I know to each of these vertices. So to this vertex, I know a path with a distance of 3, basically go from U to V and from V to this vertex. To this vertex, I know a path with a distance of 5. To this vertex, now I used to know a path with distance 6, but now I know a path with distance 2. So I can update this one to 2. Okay. And now I do the same argument again. I say among all the vertices that don't have a check mark, among all the vertices whose distance is not finalized, find the one that has the smallest distance, this one. And this distance is never going to decrease. So I'm going to put a check mark on this one. I'm going to say the distance to this one is finalized. And then I'm going to update the distance to all of its neighbors. So I look at all of the neighbors of this vertex. Let's say I have, I don't know, 2 to this, or say 1 to this. So the distance here becomes 3. And let's say I had an edge from here to here, and this one was 1. So the distance to this one also becomes 3. And so on. So every time I just look at all the vertices that don't have a check mark, all the vertices whose distance is not finalized. I pick the one with the smallest distance so far. I say you're finalized, and I update the distance to all of the neighbors. Okay. You have to prove that this algorithm is correct. You can do it by induction. Okay. And also in cases like this, when I have several vertices with the minimum distance, it doesn't matter which one I take. Okay. But this one also gives me a shortest path tree, right? Because I can say, well, let's create a tree in which I only keep the edges that gave me the shortest path in my algorithm. So this edge gave me the shortest path from U to V, remember? And then this edge gave me the shortest path from V to this vertex, and also from U to this vertex, right? And then let's say the next vertex that I finalized was this one, so this edge gave me that. Let's say the next vertex I finalized was this one, and I can finalize it only from this side, right? And finally, let's say I have this. So the red edges here are actually giving me a spanning tree. And again, as an exercise, you have to prove that this spanning tree is a shortest path tree, meaning that if I give you any vertex V and I ask you what is the shortest path from U to that vertex, it's the path in this red tree. Great. Now, we have very little time. I want to talk about one more topic today, and that's the topic of matchings. What is a matching? A matching in a graph is a bunch of edges that don't share any endpoints. So a matching M, a matching is just some set M, subset of edges, such that no two edges in M share an endpoint. So if I want to give you an example, let's say this is my graph. And I'm going to just choose two edges, this edge and this edge. And I'm going to say that M is just the red edges here. And as you see, they don't share any vertex. So every vertex is on at most one of the edges. So I call this a matching. Now, my matching doesn't have to cover all of my vertices. So if I had this graph, the same set of red edges would still be a matching. So it's just a bunch of edges that don't share any vertex. Okay. So now I can talk about maximal and maximum matchings. And this is something that's it's cute, but very obvious. So I say M is a maximal matching if I cannot add any other edge to it. Matching if there is no other matching M prime such that M prime is a superset of M. Okay. Superset is the opposite of subset. So for example, if I have, let's say this graph, right? And if I have this edge on its own is not a maximal matching because I can also add this edge, and this is a bigger matching that contains the previous matching. But if I have both of these edges, then it's maximal because I cannot add any more edges. Okay. Now, we have another definition, which is maximum, and we say that M is a maximum matching if it's basically bigger than or the same size as every other matching. If for every other matching M prime, we have that the size of M prime is less than or equal to the size of M. Okay. So these two are not the same. every maximum matching is definitely maximum. Because if I'm maximum, I have the largest possible size, so you cannot add any other edge to me, right? So that's obvious. Every maximum matching is maximum. But not every maximal matching is maximum, right? Again, as a simple example, consider this. Consider this graph and this matching. This is a maximal matching because I cannot add any more edges. But it's not a maximum matching because I have this other matching that is bigger. Okay. Great. Now I can define something called an alternating path. So let's say, suppose M is a matching in G. An alternating path, or actually an alternating walk, is a walk such that the edges are alternating between being in the matching and not being in the matching. Okay, so an alternating walk, let's call it UV walk, is a walk, I mean, it's in the name, that alternates between the edges in the matching and the edges outside of the matching. Okay. So let's say this is my matching, and let's say this is the rest of my graph. I can find an alternating walk here. I can say, take this edge which is not in the matching, then take this edge which is in the matching, take this one which is not in the matching, take this one which is in the matching, this one not in the matching, and this one which is in the matching. So basically, the red edges are the edges in M, my matching. The black edges are the edges that are not in M. And I'm just finding a path that takes black, red, black, red, black, red. Or it can also start with red. It can be red, black, red, black, red. Right. This is called an alternating path. And then I'm interested in a particular type of alternating paths or alternating walks. And these are the walks that start with black edges. Okay. So I call these ones augmenting. So an augmenting walk or an augmenting path is an alternating path that starts and ends outside of the matching. Okay, so again, let's say this is my matching. And let's say I have a path that starts outside of the matching and it's alternating, takes one edge of the matching, takes one edge outside, one edge inside, one edge outside, one edge inside, and then. Okay. So look at this path. Okay, and I can have other edges. So I'm not drawing all the edges of my graph. Suppose that there are some other edges that I don't care about. If I have a path like this is a path that is, again, starting with an edge outside of the matching and then alternating. But then it also ends with an edge outside of the matching. I can use this path to increase the size of my match. How can I do this? Just swap the colors, right? Take every black edge here, make it red. Take every red edge, make it black. You get a matching, you get a set of red edges, which is still a matching, but it's going to be bigger. So this means that if I have a matching And if I also have an augmenting path for this matching, then my matching is not maximum. Right? Here's the theorem. I want to say that a matching M is maximum if and only if it does not have an augmenting path. This is actually a theorem by Berg. Okay, and very importantly, I'm saying maximum, not maximum. Okay. One side of this theorem is obvious. If I have an augmenting path, I know how to get a bigger matching, so my matching is not maximum. Right? But the other side is not so obvious. If I don't have an augmenting path, then if I don't have an augmenting path, then my matching has to be maximum. Why? So here's the proof of the non-trivial part. So proof, I'm going to only do the non-trivial side here. So suppose that I have a matching, let M be a matching. And suppose that it's not maximum. So it's a non-maximum matching. I want to prove that I can always find an augmenting path. Okay. Well, if M is not maximum, there is some other maximum matching in my graph. So let's take that. Let M star be a maximum matching. Now I'm going to say, look at only some particular edges. Look at the edges that only appear in one of M and M star. Okay. So let's say I define some set F, subset of edges, and I say that F is M delta M star. This means I'm only taking the edges that are either in M and not in M star, or are in M star but not in M. Okay. And look at the graph. I don't know what to call it. Let's call it H, which has this set of edges. What is the degree of every vertex in this graph? It's either 0, 1, or 2. Right? Because if I look at some vertex V, at most one edge that came to V was in M, and at most one edge that came to V was in M star. Right? And I'm taking only the edges that were in one of M or M star. So the degree of this vertex V in this new graph H is at most 2. But we had a theorem. What was our theorem? We had the theorem that if I have a graph in which the degree of every vertex is at most 2, then that graph is just a bunch of cycles and paths, right? Every connected component of this graph H is either a cycle or a path. Okay. So I can look at the connected components of H, and I can have cycles. So let's say I'm using red for one of my matchings and I'm using blue for the other matching. Okay. So if I have a cycle, can it be an odd cycle? No. Because again, if I have a vertex V and if the degree of this vertex is 2, then one of the edges was in M, one of the edges was in M star. So whenever I have a cycle and I'm going around the cycle, the color of my edge should change every time. Remember, I'm showing M with, let's say, blue, and I'm showing M star with red. Right? So my graph is not just a bunch of cycles and paths. I additionally know that all of these cycles are even cycles. Okay. But what else do I know? If I have an even cycle, it's going to have the same number of blue and red edges. But M was not maximum, M star was maximum. So M star is bigger than M. So I should have more red edges than blue edges. That tells you that I have a path that has more red edges than blue edges. Right? So I'm going to have a path in this graph H that starts with a red edge, then has a blue edge, then another red edge. Basically, it's an alternating path, right? But it's going to also end with a red edge because I have more red edges than blue edges. So I have to have a path that starts and ends with red edges. Well, this is an augmenting path, right? So just use this to augment M. So I took a matching that is not maximum and I found an augmenting path. Of course, if the original matching was maximum, there could not be any augmenting path. So a matching is maximum if and only if there is no augmenting path.